Today we're going to get into two more tests, the integral test and the P-series test. We'll be on page 216 in your workbook. So the integral test, there's some conditions that have to be met first. The function has to be positive, it has to be continuous, and it has to be decreasing for all values x greater than or equal to 1. You're going to want to state this before you use the actual test. It's not necessarily something where you have to demonstrate it, but you definitely need to check for it, because if these conditions don't exist, you can't use this test. You got to use a different test. In this case, we have the sequence a sub n and the series equals some function. Basically, what the integral test says is if this series and this integral, either they are both going to converge or they're both going to diverge. Now notice here we have an improper integral here, as one of our limits of integration is infinity. So that means we're going to be dealing with limits. So yeah, there's this if and only if relationship regarding convergence and divergence between these two things. It does not, however, that those two things are equal to each other. Okay, that's not what this is about. It's not about what the value is. It's about convergence and divergence. So let's just look at some examples. We're going to look at these three. What's important again is to state those conditions. So to first tell, is this positive? All right, well, when I start plugging values in, I get 1/2. Well, I actually don't even need to plug values in. The only way this couldn't be positive is somehow this denominator went below 1 or below 0, which it can't because this is a positive number, so I'm taking a positive plus 1 every time, so these are definitely positive. In terms of being continuous, this can never be -1 because that's how we'd get 0 down here, so we're good on continuity. And then lastly, decreasing, so this is going to be 1/1/2, then for 2, 1/5, then for 3, 1/10. So those denominators are getting bigger, which means the overall value of that fraction is getting smaller. So we're good with our conditions. F of x, in this case, 1/n² plus 1, is positive, continuous, and decreasing. So what we're going to do is we're going to take the limit of this from 1 to infinity, of the integral from 1 to infinity. So that's all we're going to do is we're going to take the limit of the integral. And if you recall our improper integrals, I may have used a or another variable, but at the end of the day, just so long as you have a variable here, you're in good shape. And so we're going to integrate this and then find the limit of that. So if you want, go ahead and do that. Go ahead and integrate that yourself, and let's see what we end up with. Hopefully you remembered this is a special one. You can't just really straight up integrate it. This is one of our trig integrals. Do you remember which one? Well, it is the arctangent. Okay, so this is the arctangent of x, or the inverse tangent of x, and we're going to integrate that from b to 1. Okay, so really what we have to figure out is what is the limit of this, because we know this. What is, I left off my little inverse. There we go. What is the inverse tangent of 1? Hopefully you remember that's pi/4. Now, hopefully you also remember your limits for what the arctangent can be. And in this case, we need to know what's the biggest value it can be, because as b approaches infinity. And so that actually is pi/2. Or we can go from -pi/2 to pi/2. So in this case, it's not even important what this is. It's obviously converging. Okay, it's converging to something. And so since the integral converges, that means the series converges. And so that's what we would say. It converges by the integral test. And that's the work you'd have to show for that. Okay. Now, some of the integrals obviously are going to be simpler than this one, but as we're starting to approach the exam, remembering some of these arctan or arcsine or arc cosine integrations is going to be important. Let's move on to the next one. Okay. Hopefully you see something interesting here that maybe you can do, what type of integration techniques you might use. But we first need to determine our conditions, okay? Is this positive? Well, n starts at 2. The natural log, of course, of any positive number is a positive number, so we're good on positivity. Is there any way this can be 0? There isn't, so we're continuous. And is it decreasing? Now here you might want to type some values in and check it out just to be sure, but rest assured that it is. All right, so again, we're going to find the limit of this. And maybe you got a feeling about how you should integrate this. I'll let you give that a shot, and then you'll come back and see if you did it right. So yep, we're going to use u substitution here. I'm going to set u equal to the natural log of x, which means that du equals 1 over x dx. And so my du is already here, 1 over x dx. So I can just straight up substitute that in. And so this ends up being the natural log of u. Now, you might be wondering, why didn't I change the integration limits? Well, I'm going to put it back, actually, and keep using these. So in this case, my u is the natural log of x. So this is the natural log of the absolute value of the natural log. And so that's why I put it back. And then, of course, we're going to find those limits again of those things. This obviously is a constant. The trick is trying to figure out what the natural log of the natural log is. And if you think about the graph, I always like to think about the graph. The graph kind of looks like this, right? And while it continues to increase slowly, it does continue to increase. And so this is going to keep increasing and increasing and increasing, and it will be unbounded, which means the limit of this does not exist, or you could say infinity. Either way, it diverges by the integral test, okay? And so this series diverges because this limit, this integral, the integral of this diverges, okay? Last one, can't ever be 0 since we start at 1, so we're continuous, positive. We're not putting negatives in here, and we go from 1 to 1/2 to 1/3 to 1/4. So we definitely meet all conditions. And this one is pretty straightforward. All right, so I'm taking the limit from b to infinity from 1 to b of 1 over x. Of course, we know that one. That is just the natural log of the absolute value of x. So then, as we just discussed, this is unbounded, so this also diverges. Okay, so that is the integral test. Let's get into p-series and what that means. So that is going to be here on the next page. All right, so first off, we need to talk about what a p-series is and the harmonic series. Okay, we'll get into that in a little bit. So here's what the p-series is. Basically, p is some positive, it's got to be positive constant that we raise n to. Okay, so any kind of situation like this that even looks like this is called a p-series because we raise it to the p power. And it's always going to be in the denominator, the n to the p power. The p-series test basically says if p, that power, is greater than 1, then the p-series converges. Now, it's important to say that it's greater than 1. I mean, we just did an example where p was equal to 1, right? We did 1 over n, and we showed that that diverged. So it's important that it's greater than 1. if it is between 0, greater than 0, and less than or equal to 1, so a fraction. Remember, this has to be positive. So if it's a positive fraction, then it diverges. Now, the harmonic series, we've actually already talked about. That was the example 3 that we just talked about. This is the harmonic series, the series from 1 to infinity of 1 over n, when p equals 1. They call this a harmonic series. I think it has something to do with wavelengths in music and sound, and I read something about a guitar wavelength that it mirrors what happens as each of our fractions get smaller and smaller and smaller, that the wavelength, if you pluck a string on a guitar or hit a note on a piano, then the wavelengths associated that mirror those numerical values in some way. I don't know enough about it, but that's the best I have for why they call it a harmonic series. All right, let's talk about the p-series test. All right, so what you're going to want to do is you're just basically going to try to get it in the right form, and so that you have a 1 over n to a positive power. And if you can do that, then you'll be able to use the p-series test. So you notice here, the first thing that I notice, this is 2 times the square root of 2, 3 times the square root of 3. So right away, since we're thinking about powers, I'm thinking about changing these radicals to rational exponents. So my thinking here is that's 2 times 2 to the 1/2. This is 2 to the 3/2. Sorry, this program is just delayed when you're probably hearing tapping and it's like nothing's happening. Well, it's same thing's happening to me. Anyway, the next one, 3 times 3 to the 1/2, which is 3 to the 3/2. So we've got this, we've got our conditions, right? We've got 1, then 2, then 3, then 4, and they're raised to a power greater than 1, which means this is the kind of series we're looking at. That needs to be 1 over. 1 over that. Yeah, that's a fatal mistake right there. Anyway, this is going to converge because the power is greater than 1, and we're in good shape. And so I need to put that back into, a couple mess ups today. 3/2 is greater than 1, therefore this series converges by the p-series test, okay? And now on this next one, we're going to have to do some manipulation. We've got radicals, we've got powers, and we'll just kind of see what happens here. All right, so this is the negative 11/3. So n to the 3rd is like 12/3. 9/3. No, that would be n to the 4th, would be 12/3. Oof, tough day. So that would be negative 2/3. So then that comes down. And so again, we're in good shape here. 2/3 is in between 0 and 1, so we can use that p-series test. I probably should have put that in there. Let's put that in here. Okay. And so because 2/3 is between 0 and 1, this series is going to diverge by the p-series test. And there it is. Those are the 2 tests. Pretty quick and easy, straightforward. It's just a matter of, again, are the conditions met to use those tests? Isn't that what we've been talking about over these different tests anyways? Are the conditions right? Which test am I supposed to use? And off we go. That's what we got.